My name is Ken Miller. I'm a professor of Earth and Planetary Sciences here at Rutgers University. And this is the American Association of Petroleum Geologists Distinguished Lecture. And it is on sea level change, past, present, and future. So I've been looking at sea level change since the early 90s, both drilling onshore, drilling offshore. Our most recent activity here offshore of New Jersey, where there's currently a seismic investigation going on as we speak, which is looking below the sea floor. And I'm actually was a shore resident, and I just did sell my shore house here. So this is going to have both a geological component. We're going to look, this is an anatomically correct view of the Lady in the Harbor, okay, in an ice-free world. If you melted all the ice sheets, sea level would rise 64 meters. So again, the American Association of Petroleum Geologists has sponsored me to go on a lecture tour, both a mid-US swing and a European swing. And there's many reasons to join AEPG, and the student chapters in particular are quite good. I'd encourage you guys to form a student chapter here because there's a lot of benefits, as you can see. Sea level. Sea level is like politics. It's all local. So this is an area of the Jersey Shore called Ship Bottom. It's located in the middle part of the state on Long Beach Island. I took this picture in 2008 right after beach nourishment. This is the same area of 27th Street 2 days after Hurricane Superstorm Sandy hit. My friend's house is here. We project that by the year about 2040, this is what this area will look like, and by the year 2100, it will look like this. There will be a fundamentally different shore as this area, which is shown in blue, has been inundated. So it's important to realize what controls sea level change. So there's global sea level change, global average sea level change, which is controlled by both water temperature. So we're raising the temperature of the planet now by about 0.8 of a degree, and that contributes a little bit less now than half of the cause of modern sea level rise. There's also the melting of ice, melting mountain glaciers and ice sheets. On longer term changes, geologists like to study, there's changes in ocean ridge volume. As ridges spread faster, they take up more volume and sea level rises. But this is a very slow process. There's also regional and local sea level changes. So regional sea level changes, the whole region around New Jersey, New York, Philadelphia is sinking, subsiding. Okay, we'll explain some of those processes that include adjustments to the removal of the last ice sheet, so-called glacial isostatic adjustments. Changes in oceanography, changes in how the Gulf Stream, its intensity change, can affect sea level in the order of 10, 20 centimeters. More locally, compaction of sediments. So the best way to explain compaction to non-geologists is if you take a bucket of beach sand and you walk across from the beach, and you walk across, and by the time you get off the beach, you'll see that there's a layer of water in there. The sand has compacted and the bucket isn't as filled. So this compaction effect can be very important locally, as we'll see. So geologists are very interested in trying to reconstruct global average sea level, particularly from the oil industry. These examples are taken from Exxon Production Research Company. This is Peter Vail, formerly of Exxon Production Research Company. This is his estimates. This is showing you a mid-Oligocene, that would be a period about 30 million years ago, sea level fall of about 400 meters. This was updated by Vail's team with Bill Hawk as a senior author to be about 160 meters, which is very difficult to do with our known mechanisms. This is still, although this curve was published many years ago, this is still the opinions of Hawk and others that there are these very large 150 plus meter sea level changes, in this case for the Cretaceous. So how do you reconstruct sea level change? The first thing you do is you have to be able to date the sediments. So we don't date them usually with radiometric dates because we don't have enough of them. We use microfossils, we use strontium isotopes to date the sediments. This can be difficult in the areas most sensitive to sea level change. Okay, it can be challenging. The second is to determine changes in water depth. These are benthic foraminifera that we use to reconstruct the depth changes that we infer. This is a section from Utah where we can see that this section is shallowing upward. This is in the Book Cliffs. But there are large uncertainties in this. And then even after we've dated the water depth changes through time, we have to remove the effects that I just told you about of regional subsidence and uplift and local changes. and get to the proper reference frame. And so our reference frame, depending on where we are, changes, just like the reference frame changes for this woman. You can see as this woman walks across this swimming pool on the pool cover, her reference frame is constantly changing. And our reference frame for measuring sea level is always changing. This is showing you different colors means areas that are going down in blue and hot colors are going up. And depending on where you are, your reference frame is always changing. So how do we approach using the geological record to determine sea level change? Well, we need to basically sample the geological record. We can drill reefs, as has been done. This is the Tahiti expedition in 2005. We can drill continental margin sections, which we did offshore New Jersey here, and it's been done by the Ocean Drilling Program in New Zealand and the Bahamas and Australia. And we also can drill deep sea sections that have basically a glaciostatic proxy in the Delta 18 record and the magnesium-calcium record. So we've done this, and we've put together several generations of sea level curves. So this is the last 120 million years, the death of the dinosaur, 65 million years, KPG boundaries here. And you can see we've reconstructed large sea level changes, but not nearly as large as what was done by Exxon Production Research. So for example, that 30 million year sea level fall we reconstruct is about 60 meters or so, not 150 meters, not 400. And certainly over the last 10 million years, sea level has been varying quite largely because of the growth and decay of northern hemisphere ice sheets over particularly the past 2.5 million years. So what we did to reconstruct those curves was use New Jersey as a natural laboratory. We drilled onshore, various places. This is the Trump Castle Hotel and Casino that we drilled nearby. We drilled offshore with the JOIDES Resolution. And in 2009, we drilled these sites here with this jackup boat or lift boat, LB Cade. And the reason why New Jersey is important is it's an area where we have very simple subsidence, we have excellent age control, and very good paleodepth control. So I'd like to take students out and show them in outcrop what a sequence is. And this is a sequence from Homedale, New Jersey, a sequence boundary. So these were beachy sediments of the so-called Mount Laurel Formation, and this is a surface of an erosion due to a sea level fall, and then sea level came back in. And these things are called, these sequence boundaries are the building blocks of our record. And we can see these in cores. I'm not going to go through this whole list, but you can see that there's something here, a big break from these sediments here to these sediments here. In this case, there's a several million year hiatus or time gap. But we can use these surfaces to basically, in dating these surfaces, to figure out when sea level fell. We can also use seismic data. So this is a seismic profile of about 1,000 meters down. These are the 3 sites that we drilled. And even if you haven't had seismic stratigraphy, you can see this pattern is called an onlap. This is called a downlap. We can see an erosional truncation in there. These are seismic sequences that have been imaged offshore of New Jersey. And these are the 3 sites that we drilled. Each of these red lines is an unconformity or sequence boundary, which we're able to date in these sediments here. These sequence boundaries, again, are sea level falls. This is the area I was just showing you. This is showing it going out across. This is the continental shelf. This is the slope. So that's about 200 meters of water depth. And we've drilled out here, we've drilled in here, and we drilled onshore. These examples are from the onshore where we have 14 Miocene, that is the last 24, from 24 to 5 million years, 8 Oligocene, 12 Eocene, 7 Paleocene, and 15 to 17 late Cretaceous sequence boundaries. Just to show you the kind of data we collect, we basically, the brown here is mud, this is fine sand, medium sand. We go out and we basically identify surfaces in these cores that we drill and bring to the surface. We are able to look at those. We're able to date them using strontium isotopes. We're able to basically infer the changes in water depth. So these are basically deepening, then shallowing upwards, deepening, then shallowing upwards, deepening, then shallowing upwards successions. And we're able to place these in context. We then try to back out all those effects I told you about. So we have the subsidence. We have that subsidence being controlled by the compaction, okay, the sediments compacting. We also have the loading of the lithosphere. So when you put a mass in the lithosphere, it's depressed. So we have to unload the sediments. And then we have to account for the fact of thermal subsidence. So we take our observed sections and we decompact them to their original thicknesses. We then remove the effect of loading, which Michelle Comans, who's the lead on this part of the talk, it calls her first reduction. And then we fit a series of exponential curves. These are essentially cooling curves. And we fit the best fit to the data. And the difference between the data and the thermal curve is a measure of sea level change and non-thermal tectonics. We're interested in the sea level change part. We tend to assume that this non-thermal tectonics part is trivial. And this just, again, shows you a little more complicated version of the same thing. It's an equation and two unknowns, sea level, which we're trying to solve for, and tectonic subsidence. This is the compaction, a loading parameter. This is the decompacted sediments. We have to plug in the water depth. And from this backstripping method, we can get a global sea level estimate and non-thermal subsidence. And this is the most recent version of our curve showing the errors going back here from the Cretaceous into the last 65 million years. You can download these data and the paper from our website. Again, this is to point out that one particular event here is about 65 meters, not 150 meters. And the story behind this is, as we know, the large ice sheet appeared in Antarctica about 34 million years ago. And as a result, much of what's the sea level variations we see since that 34 million years was controlled by variations in the Antarctic ice sheet. Over the past 2.5 million years, those sea level changes have gotten even larger because we have a northern hemisphere ice sheet, a very large one, the ice ages. So the ice sheet came down to Nebraska or locally around here to the Woodbridge Center Mall. It has always been assumed that if we go back in this area that's here in orange, the Eocene, or going back into the age of the dinosaurs, the late Cretaceous, that the world was ice-free. But the only mechanism we have to explain these large sea level variations, and these are on the order of 25 meters, okay, are changes in ice volume. So this figure kind of summarizes the known mechanisms for what causes sea level changes globally. And what's shown here is the rate of the process in millions of years and its amplitude. And so the only large, rapid means of changing sea level, more than tens of meters per million years, are changes in ice sheets. So we pondered over this for a while. It's been kind of known that the Antarctic ice sheet probably did not exist as a continental-sized body until 34 million years ago. So this is about 34 million years ago, and it's showing you a map of Antarctica where red is 4 kilometers of ice, which is what we find in Antarctica today. And so these maps were reconstructed by Rob DeCanto and Dave Pollard. And they gave us a means of envisioning what the world may have been like if we went back into these so-called greenhouse worlds with warm climates and were mostly ice-free. So this would be a sea level change of about 25 meters. This would be about 15 meters. And that's kind of what we reconstruct for back here in the Cretaceous. And that's what we thought would be a best example of what we would think the so-called greenhouse ice sheet would look like. So this animation is from DeCanto and Pollard, and it's showing you a beat. See the beat back and forth? That is the heartbeat of Milankovitch. Milankovitch are the minor variations in the Earth's orbit that control the ice ages. And it's showing you this beat in the ice sheet as it grew in the late Eocene into the earliest Oligocene and became a continental scale ice sheet. For people in oil industry, they're very interested to see what does our record say about the published records from basically Exxon and other companies, mostly Exxon. So the Exxon curves of various generations are shown here. And what we find is that the timing of their falls is more or less what we observe. But the amplitudes of their falls are much too high. And in particular, so I've taught a generation of students that sea level in the Cretaceous, during the peak of the dinosaurs, 100 million years ago, 80 million years ago, sea level was about 250 meters above present. And that's probably dead wrong. And in fact, what the Exxon curves did was assumed that that was the point where sea level was at that time and scaled sea level changes to it. So we still don't know very well what the long-term sea level record is. So in 2005, we published our first synthesis paper of sea level change. And by 2008, at least 3 or 4 studies had placed New Jersey with a target on its back and said, New Jersey is not a place to study sea level. Because here's an example. This is one reconstruction of sea level by Dietmar Muller's group in Australia. And so he has sea level at about 175 meters in the peak in the Cretaceous. This is the Cretaceous. Okay? And we are much lower than that. And these papers pointed out that a breakthrough in explaining in geophysics basically surface topography, that is, and sea level changes, is the fact we know that deep in the earth in the mantle, there are plates, as they subduct into the earth, affect the surface. This is so-called mantle dynamic topography. And it explains some of the differences. And we'll come back to that in a minute. And as for people who are particularly interested in the geology, where was sea level in the Cretaceous? The best estimate would be about 150 meters for a peak. But our error bars are large. It's anywhere between 100 and 200 meters. And that's the so-called take-home, the QED, that sea level change for the peak due to these small spreading rate changes was about 150 meters above present. So we start to go into the younger record. We can use oxygen isotopes to try and get at the sea level record also. So now here's the thing. Oxygen isotopes record both temperature and changes in the seawater delta, it's called delta 18, that are due to ice volume changes. So there's, again, 2 unknowns there, temperature and ice volume. So what we did initially, Jim Wright and I, was we just took the delta 18 records and made certain assumptions about temperature. And this is more or less, this is about 80% correct. That sea level at the last major glaciation was about 120 meters below present, and basically during the last major interglacial was about 5 meters above present. So we have an excellent chronology of sea level changes. In terms of the amplitudes, this is probably about 80% correct, but that means it's probably 20% wrong because we don't know the temperature changes. But we can use another method to get at temperature. So magnesium calcium is a means, if you measure them in our foraminifera, in the calcium carbonate skeletons or tests, can be used as a paleothermometer. So this is from Ben Kramer's work showing you what a best oxygen isotopic synthesis would be for the past 65 million years. This is showing his synthesis of magnesium calcium. He removes the temperature, and the residual, what's left over, is a measure of sea level change. And he concluded in this paper that on the 2 million year scale, the New Jersey record of sea level change is pretty well, very much the same as what's observed from using this method. But what Kramer did, he smoothed everything to longer than 2 million years. So we want to look at things that are more like on the order of a few 100,000 to a million or so years. And so what we did is went back and took published data, including some new data that we generated at Rutgers from R.D. Balyut, and put together a record. So this is going from 35 million years ago to about 10 million years ago. And so both temperature and ice volume changes are in this. We use magnesium calcium to get a paleo temperature record. So we basically have coolings and warmings here. And we then use that to extract and create a oxygen isotope magnesium calcium based eustatic estimate. This is what this curve is. So it's showing you, here's this mid-Oligocene event about 30 million years ago. It is showing you about a 65-meter change in sea level, which is exactly what we observe from our other proxy from studying cores in New Jersey. So if we overlay these two, you can see the black is the New Jersey estimate, and independent is the estimate from the delta 18 magnesium calcium method. And so in here, I would argue that these are very much the same. In this interval here, we're only sampling part of the record, the so-called high stands. We don't get the low stands and much of the transgressives onshore, but we get that offshore. What's interesting is, so one of the good papers in this topic was entitled, a great title, There's No Such Thing as a Stable Continent by Rob Mucha. And Rob modeled changes in mantle dynamic topography. And what he showed is that there are changes in the order of tens of meters that occur on millions of years time scale. But one of the predictions in his model is that there'll be a difference between onshore New Jersey and offshore New Jersey of about 30 meters. So coming back to our offshore work, we drilled these sections in 2009 using the lift boat Cade and commuting via crane to get onto this crazy contraption. We got great core recovery, and this, not to take you through the piles of data, but this is just an example. This is a sequence that is bounded by surfaces of erosion, sequence boundaries. Within that sequence, we have beautiful core recovery. We have changes from sands to muds and back to sands again that represent low stand systems tracks, transgressive systems tracks, high stand systems tracks. We have excellent age control provided by strontium isotopes, but also by dinoflagellates, diatoms, nanofossils. And we have excellent paleo depth control from benthic foraminifera and from looking at the facies themselves. And so we backstripped, did the same thing offshore that we did onshore. And the onshore is shown in black, and in the offshore is shown in these colors. And you can see from this interval where the times overlap, the offshore and the offshore are offset by about 30 meters. This is exactly what was predicted by the mantle dynamic topography. What it says is, it kind of helps explain for the first time. We have a mechanism that explains some of the records that we see along the eastern coast of the United States. Delaware or North Carolina, some of the records look virtually identical to each other and to New Jersey. In other periods of time, they look very different. There are time gaps in one place, but sediments in another. So this is a mechanism, these changes in mantle dynamic topography, that can explain that. So perhaps the most relevant, as we're moving into human scale issues here, is if we go to the Pliocene in particular, this is about 2 million to 5 million year range. If we're in Virginia, okay, in this area here in Virginia, the estimates of sea level, that global sea level would have been about 20 meters higher than present. If we go to New Jersey, we have just gravels and there's no marine sediments, and sea level was probably a little bit lower even than today. So how do you explain this? This was pointed out in a paper in David Rowley. And this is showing you his model of mantle dynamic topography, showing how the differences between, let's say, Virginia and New Jersey can be explained by these changes. And this is important because the Pliocene, if we go back 3 million years ago, the Pliocene was a warm period of time. And sea level sat, well, we didn't know where it was. Was it 10 meters higher than present or 30 meters higher than present? It was thought it could have been as much as 35 meters. We got involved in this by doing our drilling in Virginia, working with people in the Wanganui Basin in New Zealand, looking at some work that was done in Enewetak Atoll, and also looking at deep sea cores. And we concluded that in the Pliocene, sea level was about 22 plus or minus 10 meters above present. Why is this important? Well, carbon dioxide estimates for the Pliocene are on the order of 400 parts per million. In 2013, we first breached 400 ppm. This year is 400 ppm, okay, on average. And in the Pliocene, it was about 1 degree warmer to 2 degrees warmer Celsius, okay? So we're going to be 1 degree at least warmer by the end of the century, more likely 3 degrees, okay? So we're looking at a Pliocene world where these ice sheets were much smaller. So again, it's telling us that when we're warming the planet, we are affecting sea level, and something to be concerned about. So people tell you, in terms of climate change, I kind of look at climate change with sea level colored glasses. And we can debate what's happening on the planet today. But we do know, people say, well, it's part of a natural cycle. Sea level rose from the melting of the last glaciers, the deglaciation starting about 20,000 years ago. 20,000 years ago to 27,000 years ago, sea level was 120 meters below present and rose, as we know from drilling this beautiful fossil coral, fossil sunshine really, Aquaporta palmata in Barbados, sea level rose in two rapid steps. During Meltwater Pulse 1A, it was rising at 47 millimeters per year. And by contrast, today, sea level is rising at 3 millimeters per year, more than 10 times higher. Slowed down during the Younger Dryas and then sped up again and then slowed as human civilization was developing beginning 10,000 years ago with the walls of Jericho. Basically, sea level was only about 10, 12 meters below present. And over the past 5,000 years, sea level has been very close to its modern position. So this raises, well, what is the record? Let's say if we go back to the time of the Romans, go back to the time of Christ, where was sea level? And the best estimate of that was provided by Andy Kemp in a paper in 2011. And he basically shows that sea level was remarkably stable during the so-called Common Era, and it rose a little bit here. But the big change, the hockey stick part of it, if you have it, is certainly in the last century. So I had to update this slide, and when I went on the road in January of this year, originally had that global sea level is rising in the 20th century at a rate of about 1.7 millimeters per year. This is derived from tide gauge data from Church and White. And it was reevaluated by Carling Hay and Bob Kopp and Jerry Mitrovica and others earlier this year, and showed that the 20th century rise, which is this curve here, is more in the order of 1.2 millimeters per year. Why is that important? Well, since about 1993, we have satellite data. And the satellite data are much more precise and have less uncertainty than the tide gauge data. And since 1993, there's a nice linear fit to this rise right now. It's been about 3.2 millimeters per year. So what this is saying is that there has been an acceleration. Certainly if we go back several thousand years ago, sea level was stable. In the 20th century, it's rising at about 1.2 millimeters per year. Today, it's rising at 3 millimeters per year, and it appears to be accelerating. And again, this is due to both thermal expansion and melting of glaciers and ice caps. So you may have heard something about the pause, that since about 1998, temperature hasn't risen as fast. Again, I look at climate change with sea level color glasses. Can you show me where the pause is in the sea level data? Okay. And basically, one of the answers is that more heat is being stored in the oceans. Anthony Watts, in his Climate Skeptics website, What's Up With That, has made fun of this problem in the sense he said, there are 63, and he keeps counting them, raising them every few days, 63 explanations for the pause. I like data. So these are data from the National Oceanographic and Atmospheric Administration showing that basically, this is the surface part of the ocean here, 0 to 700 meters is in red, going down to 2,000 meters is in black. My PhD is in oceanography, and oceanographers thought that it took longer to warm that interval in the bottom part of the thermocline, from 700 to 2,000 meters. It took longer than what's observed here. In other words, we're storing more heat in the intermediate depths of the ocean than we ever expected. So there are many other possible explanations of the pause. This is actually what I think is probably one of the best explanations. But coming back to why global sea level is rising today, some of it's the temperature component, but about a third of it is due to melting of mountain glaciers. So I like to ski, and so if I wanted to go skiing today, this is June, okay, I can just get on a plane, and I don't have to go to New Zealand. I can go to Mount Hood, or I can go to the snows of the Alps of Switzerland because the mountain glaciers are there. By 2050, I might not be able to do that. We can see that whether or not we go to the Alps of Switzerland or the Alps of New Zealand, the so-called Southern Alps, from Chile to the snows of Kilimanjaro, all these mountain glaciers are in recession. By mid-part of the century, it's very likely that Glacier National Park will not have a glacier. So these are dramatic human features. However, if you add up all those mountain glaciers, they would raise sea level by about that much. Okay. If you melted, a great quote from Inconvenient Truth, if Greenland broke up and melted, or if West Antarctica broke up and melted, this is what would happen. And he illustrates a 5 to 7 meter rise in sea level. The East Antarctic ice sheet shown here, that is 53 meters of sea level. it has huge thermal inertia. It is not melting away tomorrow, next year, next century. It takes hundreds to 1,000 plus years to really make a dent. That's why it's so interesting looking at the Pliocene world. What melted in the Pliocene world? Well, Greenland broke up and melted. West Antarctica broke up and melted. But in order, and that gives you 12 meters. In order to get to our 22 meters, you have to melt some of the East Antarctic ice sheet. We think it's this section here. This is melting that we observe in the surface today. This so-called Cook Glacier area, or the Wilkes Subglacial Basin as it's known, is probably most cutting-edge science is showing you that this is the area which will also contribute to sea level rise. So Niels Bohr, some people attribute to Mark Twain, said prediction is difficult, especially if it involves the future. So we hear of having to use climate models. I don't trust those climate models, okay? These are data. These are observations, okay? So let's go to Greenland. This is 1995 to 2010. What's going on, folks? It's decreasing, right? The data are clear. This is basically 270 gigatons per year of loss. First time I looked at this, I didn't quite get it either. So this is gigatons per year. So if you put a line on a plot of something per year, a straight line on this plot is an acceleration. Are you with me? So we are putting a line on this plot. We have an estimate of how much is accelerating. West Antarctica, it's more difficult to tell. Is it accelerating? This is accelerating. I think you would agree. You can see a straight line fits that very well. Here, East Antarctica. So East Antarctica has huge, again, thermal inertia. It's hard to change, okay? So it goes up and down. And in fact, in a warmer world, certain models predict it will have more snowfall and then actually a little bit bigger, and other models suggest something. I don't care about the models. Just look at the data. So if you take that data and you project it forward, this is what you get. This is from the National Research Council in 2011. They get about an estimate of about 82 centimeters by the year 2100, with large errors. By the way, it's very difficult to get less than 50 centimeters. It seems very unlikely. The higher end scenarios are over 135 centimeters. That is over 1.3 meters. That's over 4 feet. Okay, there's 4. The feet are on here too. So that's the best estimate projection. We redid their estimates in our paper, and I'll show you those numbers in a minute, using these updated data. This was done with a little bit older data. And we get slightly lower, but not much. But the bad news, at least for people in regions like New York, like New Orleans, like Bangladesh, is these regions are sinking. And this shows you. So this is the New York tide gauge data. This was the previous global estimate. And the difference between the two means that this region is sinking. And the bad news is Atlantic City is sinking even faster. So we're going to go into what's causing this. So New York saw 12 inches in the 20th century. Atlantic City saw 16 inches. So what this is what's so-called glacial isostatic adjustment. You could think of it as a seesaw effect. So you have the heavyset person on the one side of a seesaw gets up. What do? You sink. The heavyset person here is a big gorilla of an ice sheet that was right here that melted away. It was 4 kilometers thick, and that pops up. When that pops up, what do? We go down. Okay? And so the areas that are being uplifted are in red. The areas that are sinking are in blue. So to try and take really complex data, kind of make it fairly simple and user-friendly, I plotted the tide gauges using colors. And so here's New York. Blue is 3 millimeters per year. Philadelphia is 3 millimeters per year. Baltimore is 3 millimeters per year. Washington is 3 millimeters per year. If we go to Atlantic City, it's 4 millimeters per year. Sandy Hook's 4 millimeters per year. And if we go down to Norfolk, which is where the largest naval base in the world is, okay, it is 4.5 millimeters per year. Why is there a difference? This is what really got me curious and interested. Turns out all these sites in blue are on the fall line. So if you go up the Potomac, just a little past Washington, this is the Great Falls. If you go to scenic Trenton, New Jersey, and you go and you look, there's a falls. Okay? This separates, we call it bedrock. It means basically crystalline or indurated mudstones from soft sediments, the coastal plain. Unconsolidated, what do those sands do? What do those muds do? They compact, okay? So this is reflecting the regional signal. This is reflecting various amounts of compaction. So what causes this compaction? Well, in Atlantic City's case, and in the case of Newport region, we're pulling huge amounts of groundwater out. And that is causing the subsidence. So we got intrigued, as I said. So if you go to Sandy Hook, New Jersey, it's out here. You can stand out here where the tide gauge is and look across New York Harbor almost to see New York City and the tide gauge. Why is this particular region sinking? So we designed an experiment to drill down here in May of last year to try to answer why Sandy Hook has that sinking feeling. And we drilled right next to the tide gauge. We found really thick, young sediments, just younger now we know than 15,000 years. So all these ones in brown are about 15 to 10,000 years. And they are compacting. So we're trying to test our hypothesis that it's the compaction of these sediments that lead to Sandy Hook having that sinking feeling. So looking forward to the future, so this is New York City, and if we look at New York City going forward, we have to add in that subsidence effect due to this glacial isostatic adjustment to seesaw. So when you add the global change and the seesaw effect, New York should plan for at least 3 feet for its best estimate. Could be as low as a little bit more than 2, but maybe as high here as 4.5 feet, or maybe even a little bit higher. One of the problems with any of these are scenarios that take the rates and extrapolate it forward, is if there's if something happens that we can't anticipate, it's probably not going to be on the better side. It's going to be on the worse side, which is why you hear a lot of people say, well, you have to plan for this. Well, if there's a massive discharge to the West Antarctic ice sheet, this could happen, we could be up here on this high scenario. This is not going to be 5 meters. It could be 5 feet. If it's not going to be 5 meters, 15 feet by the end of the century. But we need to plan for upwards of over 3 feet. So to put this in context, so this is my shore house from the December 1992 northeaster. It was an island in Barnegat Bay. And then my house, that was a 100-year storm right when I bought it. And the following year we had, the previous year actually, we had a 100-year storm, okay? Yes, that was the Halloween storm. There was a 100-year storm in 2005. And of course, a couple years ago, a nasty lady named Sandy came to visit, and that was much more than a 100-year storm. In fact, that just shows Sandy, there's the 100-year storm. Sandy was a 1.5 foot surge above a 100-year storm. But to put this in perspective, so this is for Atlantic City, what the flooding of these storms was. So the 100-year flood mark, which was achieved essentially in Superstorm Sandy and in this northeaster, would have reached to about this point, 9 feet above mean lower low water. The whole idea, what is a 100-year storm? Just most folks understand this, but just let me explain it very simply. It doesn't mean it happens once in 100 years. It means in any given year, there's a 1 in 100 chance of a storm reaching that flood level. So there are 10-year storms. So that a little northeaster came through, and people in the Northeast will remember this because we're huddling without power, and the snowstorm came through this northeaster. And by the way, it flooded that far up. It flooded that far up. So that's the flooding we have to deal with today. If we come back in using our estimates in 2050, sea level will be about 1.5 feet higher. And so that little storm will have the flooding power of what was now a 10-year storm. Sandy would go way over a 100-year storm. And if we come back in the year 2100 with our best estimates of about 3 feet of rise, that little 100-year storm will have the flooding, that little northeaster typical storm of once a year will have the flooding power of a 100-year storm. So I'm not going to summarize the talk. I talked about, I like to put things on different time scales, especially as a geologist. So some geologists really care about long time scales. And so it is very interesting that during the peak sea level, 80 million years ago to 100 million years ago, sea level, well, was it 100 meters above present or was it 200 meters above present? The answer is yes. That's our error. On our million-year scale, in the greenhouse world of the late Cretaceous to Eocene, from 100 million to 33, 34 million years ago, we had ephemeral Antarctic ice sheets. That is, they came and went. They probably were here for 100,000 years or so, and then they disappeared for about 2 million years. The beat here is about 2 million years. Beginning about 33, 34 million years ago, we had these large variable Antarctic ice sheets. And the dominant beat we see is about 1.2 million years. This is what we would call a long tilt cycle. Okay? From about 2.7, 2.5 million years to present, we've had these northern hemisphere ice ages. Okay? And they cause some very large sea level changes. On a more human scale, over the past 10,000 years or so, sea level was globally rising slowly from 5,000 to 2,000 years ago. Over the last 2,000 years, it has been stable. So the answer to your question is it part of a natural cycle, as posed by Vice President Gore? And the answer is no. Okay, almost unequivocally not. In the 20th century, it was about 1.2 millimeters per year. It had accelerated from essentially 0, and today it's about 3.2 millimeters per year. So I'm going to end with a story. And the story is this. There was a symposium at the Geological Society of America a number of years ago. It was called by a number of climate skeptics. And I consider myself a skeptical person. Show me the data. So I submitted an abstract, and I basically gave a very similar talk to what you just heard. It's much shorter. But it became a really raucous debate. There were 500 geologists in the room, and there was very emotional, and there were people yelling and screaming. And this is my concluding slide. I said, should I sell my shore house? Which the answer was I actually did, but not because of sea level rise, but because it is difficult to maintain a house in a shore environment. Sandy woke me up to that fact. But I said, don't sell it, insure it. Okay? If you're planning, if my son is planning to buy my house and keep it to 2,100, well, he's better plan for another 1 foot to 3 feet of rise. What that's going to mean is more beach erosion, more rollback at the beaches. There's debate about whether or not we should be spending millions of dollars per mile to nourish our beaches, to bring the sand from offshore. If we don't do that, they will disappear. So it's we can have a political and ethical debate about that. But if you want to support the economy that supports, you have to do this. We've spent $1 billion in New Jersey so far since 1940 when we started doing this. Okay? We will be spending many times that going forward. We will lose marshland. In the area around here, we'll be losing 2 to 3% of the marshland. Okay? My house is built on a marsh. Okay? We will fortify. We can protect, but we will be losing habitats. I didn't talk about increased storm intensity, but if I did, I would just leave it with a question mark. We don't know if storms are going to get more intense or not. And I left with this slide. And so I'm walking out, and a guy literally grabbed me from behind, spun me around. He goes, what kind of way to end the talk is that? I'm like, what do you mean? He goes, well, you know sea level rose a foot to foot and a half in the 20th century and is accelerating. And he goes, what will you tell your kids? And I said, or grandkids. And he said, this is the ethical question. And I had to agree with him. I said, you're right. And it brought back, when we first published our sea level story in 2005, they did a satellite NPR show on it. And they basically, the very first middle segment was about we did about what sea level was doing. The last segment was like what the Dutch are doing to fight back. But the first segment, they went to Vanuatu. So Vanuatu is the formerly called the New Hebrides. And one of the criticisms of the Al Gore movie was that there have been no climate evacuees. He said people have been evacuated. Well, Tega Island in that year was just evacuated. It was one of the atolls in Tega. And so they asked the 2 scientists from Vanuatu, and they interviewed them for about 20 minutes. And they basically ended with this question. They said, what would you say to folks back home in America? So Vanuatu island chain in the South Pacific, former New Hebrides, the island of Tega was evacuated. And they asked the scientists from Vanuatu, they said, you have almost no carbon footprint. when the United States at that time was the largest carbon footprint on the planet, we're now number 2 behind China. They said, but what would you say to folks back home in America?
That's the only thing that I would like to say for all those who are listening, that think of those that are coming behind your children or your future generation.
Jotham Napat and Brian Phillips speaking to us from Vanuatu in the South Pacific. In a moment, we'll move stateside to hear from Rutgers University geologist Ken Miller.
Well, you've heard from Ken Miller, so now I can shut up. And this again was sponsored by the American Association of Petroleum Geologists and also the Rutgers Core Repository and Integrated Ocean Drilling Program. Thanks.